Okay, welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're looking at Gibbs free energy today. And Gibbs free energy, we're going to use Hess's law. I said we're going to come back to it. In order to show that, I will include in here the appendix right here. So this is the first page. If you need to, you can click on it and blow it up to make it larger so you can see the values. So that's the first page, the second page, and the third page inside of there. Alrighty, good. Now, Gibbs free energy is defined as the means between the spontaneousness of a reaction. Will the reaction happen on its own? The larger the number, the more it will, the less the number, the more it will not. And negative values, so the more negative it is, are spontaneous, where positive are non-spontaneous, so they're less likely. So if I've got a positive value that's really big, it's really not likely to start on its own. All right, now we're going to use Hess's law. So let's show what we're talking about here. Let's determine the Gibbs free energy for the reaction of methane. We'll keep it easy with oxygen. Methane, you should know, is CH4 plus O2 combustion reaction, generates carbon dioxide and water, balancing it up. We put a 2 in front of the oxygen, 2 in front of the water. So we have here methane, and the delta H from that list, and there should be an F there, formation, is negative 74.8, and the Gibbs free energy formation is negative 50.8. All right, now for carbon dioxide, it's negative 393.5 and 394.4. For water, it's of liquid water, it's negative 285.83 and negative 237.13. Again, all these values are kilojoules per mole. I didn't write those down. You need to know that. All right. So what we're going to do is going to do the Hess. First one, the reaction's flipped. So the value is going to be 74.8 and 50.8 because it's flipped. It's no longer negative. And we don't have to multiply by 2. We just leave it as is where it is. Carbon dioxide can be dropped down. It's the same side, not multiplied by anything. So the value is negative 393.5 and negative 394.4. Now water, again, we have to multiply by 2. So we'll take our value of 285.83 negative times 2 and get negative 571.66. And do the same thing with the Gibbs free energy. Negative 237.13 times 2 is negative 474.26. Again, these are all kilojoules per mole. We're going to add them up. My carbons cross out. My H2s, my hydrogens cross out. We're left with 2 oxygen, so that's what we have. Bring our first value down. We didn't ask for that one. Add the second one, and that's the answer we want. So the Gibbs free energy here is negative 817.86 kilojoules per mole. This is a spontaneous reaction. All right, that should be straightforward. It's pretty good. Now let's take a look at another value. The value we call delta S. Delta S is entropy. Entropy is defined as the measure of disorder in a system. If you take your room and don't clean it, what will happen eventually is it'll become a mess. That's entropy, from order to disorder. We have what's called the second law of thermodynamics. The reason why I don't believe in certain theories of biological sciences is because of this one. Go from order to disorder, not disorder to order. Okay, what does the second law of thermodynamics state? In the universe, substances go from a state of order to disorder, and that's straightforward. It's a law. Doesn't matter if you like it or not, it's a law. All right, so how do we find it? We could use Hess's law. It doesn't quite work that way. So we're going to have to use what is called the Gibbs free energy equation. Delta G is equal to delta H minus T delta S. Now, remember, delta H means its enthalpy is negative, it's exothermic. If delta S is positive, then my reaction is always going to be, and a positive delta S means it's going to an increased disorder state. If that's the case, if we have decreased order and it's exothermic, the reaction is always spontaneous. If, on the other hand, it's endothermic and it's going to increase order, it's never going to be spontaneous. It's always going to be positive. What do we do if they're switched? Well, it depends on the temperatures. In situations, high temperatures, they'll be spontaneous. Other situations, low temperatures, be spontaneous in the values. So let's take a look at that last problem. If we're trying to find a equation here for that last problem we just did, take our Gibbs free energy and our enthalpy, that's the reason why we solved it, and we say those values, delta S is going to be equal to delta G minus delta H. Rearrange the equation, divide by negative T. We need a temperature, so we're going to say the temperature is 38.9 degrees Celsius. We need that in Kelvin, so it's 311.9 Kelvin. Put our values in, negative 817.86 minus a minus 890.36, divide by a negative 311.9, and we're going to get negative 0.2324 kilojoules per mole. I don't like decimals. I'm going to move it to joules. 3 places. There we go, that way. 3 places to the right there, and we're going to get a negative 232.4 joules per mole Kelvin, and that's my entropy for that reaction. So let's try another one. Calculate the entropy of Gibbs free energy and the entropy of the reaction of ethane C2H6 with oxygen at 67.97 degrees Celsius as a product of water is a gas. We're using water this time, it's a gas. All right, so there's our reaction. C2H6 plus reaction plus oxygen is CO2 plus H2O. Balance it up. We have 2C2H6 plus 7O2 yields 4H2O, CO2 plus 6H2O gas. All right, now, from the appendix C, we have those 3 delta H of F and delta G of F. Remember, these are all kilojoules per mole. So what we're going to do is going to take the first one, flip it, and then we're going to have to multiply by 2. So it means we'll take our values and multiply by 2, but because they're flipped, instead of being negative, be positive. And so we'll get 169.36 and 65.78. We don't have to worry about oxygen because oxygen is an element. So carbon dioxide, we'll multiply by 4. So take our values, each of these by 4. We're not going to have to flip it. So the values will be the same. 4 times negative 393.5 and 4 times negative 394.4 is negative 1,574 kilojoules per mole and negative 1,577.6 kilojoules per mole. And then for water, we're going to multiply by 6. So take our values and multiply by 6. So we get 1450.92 and negative 1371.42. Add them all up. Carbons cross out, hydrogens cross out. We get the reaction we want. So our delta H of F, which we're going to need to solve for Gibbs, for entropy, is negative 2,855.56 kilojoules per mole. Really exothermic, giving off a lot of heat. And negative 2,883.2456 is my, get rid of that decimal point there, is my, I'm not sure what that is. Let's get over there. Is my Gibbs free energy. All right. Now put them into the equation. All right. So there we go. Multiply through. Convert to joules. And there's our answers. All right. So this time I'm going to give you the reaction here. And I will give you balanced. And then there's the delta H of F and delta G of F. Work through it, pause the video, see if you come up with the answers. Okay? All right. Those are my answers, my delta G, my delta H. And for delta S, plug it in, we get negative 85.37 joules per mole Kelvin. All right, one last problem then. Okay, try this one on your own, completely on your own. See if you get the answers. Again, go back and pull up Appendix C so you get the value, pause it, download, screenshot, whatever you need to do. All right, if you have any questions, remember to email me. All right, here we go. There's the answer. Delta H, negative 378 kilojoules per mole. Delta G, negative 384 kilojoules per mole. And delta S, 20 joules per mole Kelvin. All right, that's it. Any questions, let me know. Take care. God bless.